All right, today we're going to look at some correlation, mainly linear correlation. There are other types, but focusing on linear today. How two things are related. Remember, correlation does not imply causation. We'll be looking at a lot of scatter plots today. This is a scatter plot basing shoe print size on the bottom with height, a person's height going up. You would expect the bigger the shoe print, the bigger the height, and it's true in most cases, but obviously it's not a perfectly straight line, so it's not completely true all the time for some people. What our job is going to be today is to figure out how well they are correlated or related to each other. Correlation exists between two variables when the values of one variable are somehow associated with the values of another one. A linear correlation, which is what we're concentrating on, exists between two variables when there's a correlation and the plotted points of paired data, your scatter plot, result in a pattern that is approximated by a straight line. It doesn't have to be a straight line, and it won't be hardly ever, if ever, but fairly close to a straight line means there's a linear correlation. We have what we call a linear correlation coefficient. It is R. We're going to look at a lot of R's in class tomorrow. R is a number that tells you how well the paired sample data fit in a straight line pattern when you graph them. Now, it's all about sample data. R measures sample data. There's another variable that measures population data, and we're not going to worry about that until we're going to come back to this later in the year, but for now, R is what measures how good of a fit your sample data is, and it's a correlation coefficient. Also, the big fancy name is called the Pearson product correlation coefficient, and that's named after the guy that discovered it, Mr. Pearson. There are correlations that are not linear, but again, today we're going to stick to the ones that are just linear. So today we're looking for lines only. Even though you may see some other patterns, today we're just interested in how close to a line our data is. Properties of R. Before I start digging into what some of these pictures look like, properties of R are very important. The value of R is always between -1 and +1. The closer to -1 it is, the stronger the relationship. The stronger the +1, the closer the relationship, or stronger, I should say. The closer to 0 it is, the weaker the relationship. The value of R doesn't matter which one you pick for X and Y. It doesn't matter which choice you put on your X-axis or Y-axis. R is going to be the same no matter what. Just talked about this. R measures how strong the relationship is. And R is very sensitive to outliers. If there's an outlier, or especially more than one outlier, it can really change. This one even says a single outlier can dramatically affect its value because it's messing up how close to a line you can make your points. So the further away the points get from a line, the worse your R, or the lower your R. Okay, here's some examples right here. The first picture, if you're looking at this one, this has a positive correlation. It's like a positive slope. It's going up there. The correlation coefficient is 0.85, which is pretty strong. That's fairly close to 1. But look at this one. This is a negative one, because like a negative slope is going down. The negative correlation coefficient is -0.96, which is close to -1. It's even closer. That's why it's a little bit tighter. The points are a little tighter, closer together than this one. That's what no correlation looks like. Correlation 0, points everywhere, no pattern whatsoever. And this is a relationship. It's like a parabola right here, but it's a nonlinear one, so your R on that one's very low. So even though there's a relationship there between the two variables, it's not linear, so the R is very low. Because we can conclude that there's linear correlation between X and Y, tomorrow what we're going to do is we're going to find the best equation we can use to predict X, or using X to predict Y. However, this is huge. A predicted value will not necessarily give you the exact result. Most predictions don't. That occurs because there are other factors involved affecting Y, such as sometimes things just vary randomly for random reasons, and also there are other characteristics not included in the study that could also affect the change in Y, not just because X changed, but we have one measure to help us to figure out how much of the change it is, and that is this, R squared. We're going to square R, and that's going to tell us the proportion of the change in Y that is explained by the linear relationship. So some of it is explained because there's a linear relationship, and that's going to tell us what percent. And I don't know if you can read this, it's very small. If I make it bigger, it won't fit on the slide. Here's an R that's 0.813. So if you square that R, you get 0.661. So what the R squared tells you is you could read it like this. We can say that 66% of the change in Y can be explained by the fact that there's a linear relationship between x and y. So not all the change, but 66% of the change in y is based on the fact that there's a linear relationship between the two variables. I'm going to show you one example here, and then we'll be done. I found a chart here on length of femurs, which is in your leg, and people's height. And you would expect the longer the femur, the taller the person. So you would expect there to be a relationship there, I guess, unless people have very, very small torsos or something. But I graphed it on my calculator, and there's the scatter plot I got. And you can tell they're both increasing pretty close to a line. I went ahead and figured out R on my calculator and got 0.96. When I squared which means that's a very strong positive relationship. And so I squared my R and got 0.925, which tells me this: 92.5% of the variation in height, or the change in height, can be explained by the linear relationship between femur length and heights. I hope that makes some sense to you. So you can explain some of it, in this case a lot of it. The longer the femur, you would think that would explain how tall people are, so that does make sense. It is a very high percentage, whereas the last one you saw was just 66. So it just depends on what R squared is, what percent of one is determined by the linear relationship between the two variables. So hope that makes some sense. Tomorrow we're going to do a lot of R's, a lot of R squares, a lot of writing sentences like this one, so be prepared for that. And I'll see you in class tomorrow. See you then.